Hey guys, I'm called Dr. Derek. Today we are going to look at solving the heat equation using the integral transform method. Thank you. The heat equation we're going to deal with today is the one where there is natural convection along the sides of the metal rod. The heat equation is stated in the slide 2 above, but to use the integral transform, we have to transform this heat equation PDE into an integral form, which is given there with the limit from 0 to infinity, since the metal rod we're going to deal with is going to be semi-infinite. Thank you. The scenario we're going to look at is a scenario where there's a flux Q at x is equal to 0. The boundary conditions are the negative temperature gradient at x is equal to 0 times the thermal conductivity K is equal to Q. And the other boundary condition is that T is equal to T infinity at x is equal to T. The initial condition is T is equal to T infinity at T is equal to 0. Before we can use the integral form heat equation, we have to postulate a temperature profile that satisfies the boundary conditions. We start with an exponential temperature profile, which is in terms of Ts. We take the temperature gradient, then we get the negative temperature gradient times the thermal conductivity K, and we equate it to Q, the flux. Then we get an expression for Ts minus T infinity as Q lambda over K. We substitute for this expression of Ts minus T infinity into the temperature profile, and we get the temperature profile is stated there in green, which is T minus T infinity is equal to Q times lambda over K times exponential negative x over lambda. The temperature profile above satisfies the two boundary conditions that at x is equal to infinity, T is equal to T infinity, and also that there is a flux Q at x is equal to 0. After getting the temperature profile that satisfies the boundary conditions, we have to look at the initial condition. The initial condition says that T is equal to 0, T is equal to T infinity. For the initial condition to be satisfied, we have to have that lambda is equal to 0 at T is equal to 0. We have to ensure that this condition is met, so the initial condition is satisfied. Having the temperature profile that satisfies the boundary initial condition, and also having the heat equation in integral form, we can go ahead and evaluate the integrals above using the temperature profile above. We start with the first integral, which is the second derivative of the temperature with respect to distance x, integrated from 0 to infinity. We shall get the solution as Q over K, but how do we get this? We start with the temperature profile, we differentiate it twice, then we integrate it from 0 to infinity. As shown in the slide, we end up with Q over K. We go to the next integral, which is T minus T infinity dx from 0 to infinity, which is given by Q over K times lambda squared. But how do we get this? We're going to start with the temperature profile, we substitute it into the integral, we carry out the integral of the exponential from 0 to infinity, and we end up with Q over K over lambda squared as the value of the integral. The last integral is carrying out the derivative of the integral of T dx from 0 to infinity. Now the solution is Q over K times 2 times lambda dt. But how do we do this? First of all, we know the temperature profile, which we got. We get an export T, which we substitute into T dx from 0 to infinity. Now we shall end up with an expression which has T infinity times infinity. But when we differentiate that expression, we end up with 0. So we carry out the time derivative of the nt dx, and we find that the solution is Q over K times 2 lambda times lambda dt. Now after evaluating all the integrals above, we substitute them back into the integral form heat equation, and we get an expression of lambda in terms of the physical constants. But recall the boundary condition is lambda is equal to 0 at T is equal to 0. We go ahead and solve using that boundary condition. We get an expression for lambda is equal to square root of Ka over hp times brackets, open brackets, 1 minus exponential negative hpt over area c, close brackets. That's the expression for lambda we've got. We go ahead and substitute for the lambda in the temperature profile, and we get the temperature profile there in terms of time, which satisfies both the boundary and the initial conditions. Now we ask, what is the application scenario of all the work we've done? Now the application scenario of all the work we've done involves heating a semi-infinite metal rod, a candle aluminum rod with a candle flame at one end, and noting the time taken for the works placed at distances x from the hot end to melt. Since the candle flame has a flux, we can go ahead and use the calculations we've used above, predict how heat will be conducted along the metal rod. Now looking at the prediction starting from the temperature profile, we arrange the temperature profile in terms of lambda. We take everything to one side and we equate it equal to 1. Then we take the natural logs of the left hand side of the equation and we end up with x over lambda plus natural log of kt minus t infinity over q lambda is equal to 0. Let's continue. Now we know the binomial expansion of natural log as stated in the slide. Now for x far less than 1, we can approximate the natural log to natural log of x is approximately equal to x minus 1. Now we also had a natural log in our solution, we got there. Now we can approximate that natural log to k t minus t lambda infinity over q lambda minus 1, provided k t minus t infinity over q lambda is far less than 1. We go ahead and substitute the expression for the natural log, for the approximated natural log, into the equation of lambda. We get k over lambda plus kt minus t infinity over q lambda minus 1. We arrange and we get an expression that x is directly proportional to lambda plus a negative intercept. Here we know the expression of lambda be given as stated there. Now looking at the expression of lambda, it involves an exponential. Now we can approximate this exponential to the first order as exponential negative hpt over area c is approximately equal to 1 minus hp over area ct. Again, 1 minus exponential negative hpt over area c is approximately equal to hp over area ct. Substituting this approximation in lambda, we end up with lambda is equal to square root of thermodifusivity times the time t. Now substituting this expression for lambda into the equation we get the expression of x is equal to square root of thermodifusivity times t plus a negative intercept. Now from experimental results, we plotted the graph of x against the square root of time and it gave us a straight line graph with a negative intercept as predicted by theory. Yeah, let's continue. Now the values got from the graph above before cannot be used to measure physical constants because we did so many approximations, so the values got will have a lot of errors. But to get the true values of the physical constants like thermoconductivity and the heat transfer coefficient, we start with the temperature profile, then we take natural logs and we get x over lambda is equal to natural log of lambda plus a constant plus an intercept. Now that is the graph we are going to plot to measure of the physical constants. Now from the graph of x over lambda, substituting for lambda, the equation looks as that. Now taking b is equal to h over r c, we can rearrange the parameters in the above equation, then we shall end up with x over square root of 1 minus exponential negative bt is proportional to the natural log of 1 minus exponential negative bt plus an intercept. We go ahead and plot the graph above and it gives us a straight line graph with a positive intercept. Now from the graph above, since it's not approximated, we can measure up the physical constants with accuracy, with high accuracy. Let's continue. Now in conclusion, we note that the integral transform is very useful in helping us describe the nature of the motion of the temperature boundary layer during conduction. Integral transform can be extended to other scenarios and other boundary conditions to use different solutions. Thank you, that's all we've had time for today. Goodbye.